right, everybody, I wanted to pick up on this slide where we left off. I think there was something I misspoke about in the previous lecture, and it was about targeting the peptidoglycan layer. I think I accidentally said the lipopolysaccharide layer. So we certainly can target that peptidoglycan layer of those gram-positive bacteria with antibiotics that specifically can be absorbed by the lipopolysaccharide layer. All right. I believe the last thing we needed to touch upon on this figure was how the antimicrobial drugs can affect DNA and RNA. So you can see here in this lower part of the figure, lower right-hand side, that we have medications like the quinolones that can inhibit replication and transcription. And they can inhibit what we call gyrase, which is an unwinding enzyme associated with DNA replication. So essentially, when that DNA opens up, and normally the bacterium would be replicating the G's and A's and the T's and C's, what can happen is these particular antimicrobial drugs are going to inhibit that enzyme so that the DNA doesn't unwind. So therefore, it's not able to replicate. And then there's another particular example there of rifampin that is going to target RNA polymerase, which is responsible for the making of RNA. So some pretty neat mechanisms or solutions, if you let me use that word, for how to target microbes and make sure that they're not overpopulating and making people sick. All right. Next. This slide is really just a summary of the previous slide. So if you'd like to have some particular notes here, then you can pause this presentation and then make those notes. Okay, this is a figure table 10.5 from a previous version of your textbook. And essentially it's giving us a comparison, if you will, of broad spectrum and narrow spectrum antibiotics. So on the table where you see a particular antibiotic that has a very long line or bar, this is telling us that they are a broad spectrum type of antibiotic. If it has a really narrow bar, then that tells you it's only going to be effective for a very narrow sampling of microbes, and so therefore are considered narrow spectrum antibiotics. So here you see the tetracyclines are effective for gram-negatives, gram-positives, some chlamydias, and rickets, or essentially not rickets, rickettsia, which is the Rocky Mountain spotted fever. Carbapenems, relatively broad spectrum, but you see not as broad, if you will, as tetracycline, but treats gram-negative and gram-positive bacteria. Of course, over here, polymyxin, just a small subset of our gram-negatives. And we have one medication down here that is a treatment for TB, so another narrow spectrum antibiotic. Okay, so in thinking about the title of this slide is Interactions Between the Drug and the Microbe. So a little bit repetitive from the previous slides, but it's a good summary slide. So drugs with excellent selective toxicity are going to block the synthesis of bacterial cell wall. So these are considered the penicillins. So human cells, we lack the peptidoglycan layer, so therefore that drug is not going to affect our cells. So remember, we're looking for a particular medication or drug that is going to be toxic to the microbe, but not toxic to our host cell. So these particular medications are good for those gram-positive bacteria. And as you remember from the slide before and the one before that, the reason why these penicillins are working so well is that they're blocking the synthesis of the bacterial cell wall, but in particular, that peptidoglycan layer is excellent to target. So the gram-positive bacteria are targeted. All right, so we know that if we have medications that are designed to target something that's similar between the prokaryotes and eukaryotic cells, for example, the cytoplasmic membrane, well, this is not the best target, if you will, of a cell because we have that in similar. So drugs that act upon a structure common to both the infective agent and the host cell can be toxic to us. Now, some medications will have some level of toxicity, which is why we have side effects associated with medications. But in general, we're trying to minimize that. And the last bullet there, as characteristics of the infectious agent are more and more similar to the host cell, then selective toxicity becomes more difficult to achieve. So if you're infected with a eukaryotic cell, then we know that it's going to be much more difficult, which is why our antifungals and some of the other like anti-protozoa medications are trickier and more toxic, is simply because we have more in common. So you have eukaryotic cells. Let's talk about biofilms. So you might remember in an earlier lecture or two that we talked about that some bacteria live in a community, so to speak. And when you live in a community, these bacteria and the biofilms take on kind of a whole different, like, I don't want to say personality, but they behave very differently. The way that we target them is different because now they are protected not only by one another and the interactions between those various species in the biofilm, but also because our biofilms have this extracellular matrix that is very difficult to penetrate. So you might remember I talked about Pseudomonas. Pseudomonas infection in the lungs. It can create a biofilm, and it's very, very difficult to treat those infections. They're almost impermeable to our antibiotics because even inside the middle, if you imagine like a ball of Pseudomonas, in the middle of that ball or that biofilm are cells that aren't even being susceptible to our antimicrobial treatments. So we have to treat those biofilms differently than we would if they were each living on their own or free living. So biofilms are a particular problem, particularly in medical devices, anything that's going in like indwelling. So you have your catheters, you have your endotracheal tubes. These things can become havens for the growth of biofilms. Now, how do we essentially treat biofilms? So there's the one antibiotic that they mentioned there, daptomycin, has shown some success. And look at this, adding the DNAase, or that's the enzyme that is going to help us replicate DNA, but adding some of those into the antibiotics actually are going to help degrade some of that extracellular matrix so that the antibiotics can get to more of the cells in the biofilm. Now, where the research has been really for the last 10 plus years is using nanotechnology to essentially add some materials to things like catheters or endotracheal tubes that essentially make them impermeable to biofilm growth to begin with. So material science is kind of where it's at with that, or nanotechnology. Okay. Moving on, so fungal infections. So probably the most common fungal infections that you know of would be things like yeast infection. There's yeast infection of the groin, of the vagina, of certainly skin, toes, and things like that. And so when we are looking for those kind of medications, they really stick out in my mind because many of them end with azoles, so the azoles. So ketoconazole, fluconazole, miconazole, and clotrimazole, which this is things that you would find in like your treatment for a ringworm, treatment for athlete's foot, or the infections of the groin. And another one that you may not be as familiar with, but this one, terbinafine, is associated with many of the groin-related yeast infections. Okay, so we know that fungi are eukaryotic. We know that they have some special features, though. They have a cell wall made of chitin, and that can be one of the agents that we target when we're selecting drugs to combat fungal infections. But we have to be super, super careful because of that toxicity to human cells, because in fact, we're both eukaryotes. So we wouldn't want to target the plasma membrane. We wouldn't want to target DNA or RNA synthesis, since that is similar between bacteria and humans. So I put a few categories of antiviral drugs here. you're often going to see them ending in vir, V-I-R. So acyclovir, valcyclovir, remdesivir. So you can see this is over and over. There are some newer fangled ones that do not end in that, but instead might end in INE. That's not always a sure thing. So if you're taking a test in pharmacology, you want to be careful about those things. But essentially, with our antiviral medications, we are trying to disrupt the viral metabolism, but not the host cell metabolism, because we know that viruses are hijacking the DNA or RNA of a host cell. So we want to be careful that we're not disrupting the actual host cell metabolism. So there's a couple of different ways to do this. You can see them here. There's the inhibition of virus entry. So this is where the virus is essentially connecting to a host cell at the receptor. So there are receptor fusion and uncoating inhibitors. So that would block the cell from actually being injected with that viral DNA or RNA. There's inhibition of nucleic acid synthesis. So this makes a lot of sense, because if they are trying to use your host cell machinery to make DNA and RNA, then we can block that. And then the last way there is the inhibition of viral assembly or release. So we're thinking like about the virus life cycle and figuring out where in the life cycle can we actually stop the ability of that virus to replicate. Now, just with our antifungals, we didn't really go into a lot of it with the antibiotics, but essentially there are side effects to antiviral medications. So I put a couple of here: side effects of acyclovir, seizures, confusion, and rash, and AZT, so immunosuppression and anemia. Now, where the science is at with antiviral treatments is really with vaccines. So vaccines work really, really well to protect us against viruses. And so there's been great advancements with that, with many of our, childhood diseases and so on, but essentially continuing to treat viruses with vaccines is really a more of a sure thing than trying to chase it with antiviral drugs. Okay, I believe the last topic is about resistance. So we're going to talk about that. But I first wanted to start with this idea of natural selection. So we know that essentially over time, organisms, whether that be eukaryotic or prokaryotic, are going to change. Their genetics will change over time depending on the environment. So this is no different than the bacteria in our bodies when we're taking an antibiotic. So I mentioned that if an individual has taken loads of antibiotics over the course of their lifetime, they themselves can have antibiotic resistant bacteria in their bodies. Certainly those can be passed on to other people in the population. But essentially, we know that when we're treating microorganisms with antibiotics, we're not killing all of them, even if we follow everything to a T. So you took your antibiotics as you were supposed to. If it was one that said take with food or don't take with food, don't take alcohol, whatever, do it, every 12 hours for 2 weeks or something, then even when you're done with that, you might still have a few of those bacteria causing still alive. And if they haven't been killed yet, then they may in fact actually be resistant to the antibiotic that you're taking. So when this happens, when we have an individual bacterium that's resistant, then it is going to divide and replicate and pass on its resistant genes. So this talks about the third bullet point: offspring inherit their drug resistance. So absolutely, we killed most of them, but not all of them. Some of them still remained, and they had this selective advantage. They had this special trait that allowed them not to be killed. So they're going to replicate and make more of themselves. So it's really just a product of natural selection that we have antibiotic resistance or antiviral drug resistance. It's not that anyone set out to do that. Of course, we've had to learn some mistakes and learn some really important lessons about what's treated with antibiotics and what's not. So where are we at? So if we go back, remember Fleming discovered the first antibiotic, and since then, Essentially, we have been running this race with bacteria because